Let's talk about EBNF. What is EBNF? Well, it's something you might want to learn if you are interested in making parsers and making your own programming languages, particularly parsers, because when I make my programming languages, or make my toy ones, I should really say, I like writing my own parsers. Now, if you watched me talk about, or if you've watched anyone really talk about making programming languages, you'll know that there are a couple stages, right? And let's go through those real quick. Stage 1, 2, and then 3. We're going to talk about and interpret the language because that's what I'm the most knowledgeable on. So step 1, we're going to feed the raw input from the user. This might be the program or maybe an expression for a calculator. And we're going to feed that into what's called a lexer. Feed input into lexer. And the lexer returns a series of tokens. What are tokens? Well, to quickly recap, tokens are basically meaningful chunks of the source input, right? And if this is a calculator, I gotta keep plugging that video I made a while ago. Those might be the operators that are being used, numbers, parentheses, etc. This is information that we need for us to be able to either calculate the result or, interpret the program if we're making a programming language. So after we have this list of tokens, we're going to feed the tokens into what's called a parser. Feed tokens into parser. And then the parser will return something called an AST. An AST is short for abstract syntax tree, and an abstract syntax tree is a diagram which basically gives us a more abstract idea of what the program or what the expression or generally what is being done, right? And so it's a way of giving you an idea of what's being said, right? And not having to look at the raw program data, right? Not looking at the program itself or at the tokens themselves, right? And when you speak to other people, when you're listening to me right now, you're actually making an abstract syntax tree in your head when you're listening. And your mind, your brain automatically does this for you so you can understand what's being said by me. So there's some interesting overlap between linguistics and making programming languages, and I can talk about that another time. Anyhow, so now that we have this abstract syntax tree, which gives us an idea of what's being said, we will feed. I can't type today. Feed the AST into the interpreter, right? And most likely this is going to be a tree walking interpreter, which basically means that in every node in our tree, I wonder if I can render this textually. Let's see how skilled I am. Now, if you remember in the example I gave when we were making a calculator, every node basically represented an operator of some type in our calculator, right? And so, boink, doink, doink, doink. So, in this real simple example we have here, we have this addition operator, and this single node right here is the top node, right? And in a tree structure, this is called a tree. The top node is called the root node. This is the node that's closest to the top and will have the most branches. And if this was a program, what we would expect is maybe the root node be a grandmaster sort of program node, where all the branches, all these lines coming off of it, would be each individual statement in our program, right? But in the case here, the root node is an operator that we need to do, right? We need to perform to evaluate some result, right? So if we look at this example, if we were to write an interpreter, what the interpreter will do is look at this top node and say, okay, we're going to be adding two things, x and y, but we don't know exactly what the values of x and y are. So what we have to do is we have to go, okay, we're going to travel down, and these lines coming off here are called branches. We're going to go down each of these branches to figure out what the values of x and y are. In this case, we travel down this branch, doink, 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 and we come to this node, which is a number node, and we have the value 2. So we say, okay, so we're saying that x has the value of 2 over here. That's pretty sweet. So now that we know that x is 2, we jump up the branch and we crawl up to the root node and we say, okay, so x is 2. Cool. Well, I don't know what y is, so we're going to go down this right branch. Doink, 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 doink. And this is another number node, and it has the value 1. So we now know that y is equal to 1. Cool. Now that we know that, we can go up to this root node and substitute y for 1. At which point, now that we have the numbers, we can perform the calculation and get 3, right? And that's how you can interpret and calculate results with an interpreter on an abstract syntax tree. And this can be more varied, right? If, for example, if this node right here, I wonder, oh no, Vim can't do that for me, I'm sorry. But say instead I could have another operator, which is like multiplication, and you could imagine that, oh, come on, Alastar, get good at typing, get good. But you could imagine that if I replace this for y again, and I actually didn't know the result this time, but you could imagine that in this case, we'd have a multiplication operator, and we have 2 more branches that we got to figure out the values are, right? Say I'm going to be super lazy and not write out the whole thing. Let's keep this simple because I'm bad at arithmetic. Okay, say in this example, right, we have these branches off of this multiplication, and on the root node we have addition, and we're saying, okay, we have 2 and we're adding 2 to some y. We don't know what y is. So we're going to travel down this branch and see, okay, we don't know what y is, and we're at another node. So we're going to say, okay, we're at this node, and we're going to be multiplying some n and m, right? We don't know what n and m are, so we're going to travel down each of the branches of this node to figure out what n and m are so we can send up a value to the root node. So we're going to travel down and go, oh, okay, we have a number here, which is 2, so we know that n is equal to 2. Pretty rad, don't you think? Yeah. So we travel up now that we know that n is equal to 2, and we say, okay, we're going to substitute this for 2. Or multiplying 2 by some number m. We don't know what m is, so we're going to travel down the other branch, find a 3, and say, oh, well, m is 3. So now that we have this information, we go up, substitute m for 3, perform the calculation, and get 6. And then up here, since we still are wondering, hey, what the heck is y, we say, oh, well, I just calculated y for you, and that's 6. So now that we're happy, we can, because we have what y is, we can go up the branch and go, okay, I now know what y is, I can substitute this for 6, and I now know that the calculation will be 8, right? I can now calculate the result. Cool. So you can, hopefully that gives you more of an idea on how this can be more abstract, right? That's all well and good, but we gotta understand, how do we actually write a parser? I'm not sure if I'll show you how to write a parser, at least a recursive descent parser, which is one of the easiest types of parsers to write. But I'll show you what one of the tools is, which can help you write down on paper to help you figure out the grammar for your programming language or whatever. Okay, and we're going to focus on something called EBNF, which I started this video kind of talking about. EBNF stands for Extended Backus-Naur form. I'm probably spelling that wrong. But basically, what this is, it's a way of describing patterns of text or information, right? So let's give a real stupid example. If anyone has any, if you're watching this and you have some familiarity with regexes, like regular expressions, then this is going to look very familiar to you. Otherwise, this might be a little wacky. So what we're going to have is we're going to have terminals and non-terminals. Okay, so let's have a super simple example. So what we're going to have is, say we want binary, right? Binary. Or we're going to have binary digit. Binary digit. Right, this is going to be a super simple example. So we're going to say a binary digit is either, let's start real super simple. We're going to say a binary digit is just 0. Okay? So this, doink, 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 the binary digit word right before the colon is what's called a terminal. And this can be used in later expressions and can help have recursive grammars. And that's really important because a lot of grammars for programming languages and natural languages too have recursive natures to them. If you don't know what recursion is, it's defining things in terms of themselves. You'll learn about it if you learn about sequences in algebra too. I love recursion. It's pretty fun. It's like saying Fibonacci is a famous example, where the fib of some number n is equal to the Fibonacci number n minus 1 plus the Fibonacci number of n minus 2, where the fib of 0 is 0 and the fib of 1 is 1. And that can let you calculate recursively any Fibonacci number. Anyhow, whoa, didn't mean to do that. Doink, 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 doink. Okay, so let's go back to our example. We have a binary digit. We're saying that it can just be the single digit 0. Okay, so in this simple example, following this grammar that I've described down here with the binary digit, what kind of text can we generate? Well, we can have just a binary digit, and that's it. That's all I can generate. I can only generate a single 0. Okay, that's kind of lame. But what if I wanted to have one or more zeros? So at least 1 0. Well, I guess in this example, I would follow the 0 after the quotation marks with a plus. The plus sign says there has to be at least 1 0, but after the 1 0, we can allow for more than 1. Okay, so that might sound a little confusing. So let's try to generate some text with this single rule that we have. Okay, so binary digit, that can be a 0. So we have a binary digit. Actually, I'm sorry, I'm being dumb. Let's say I'm being big dumb. We have a binary digit which can only be 0. We're going to make it into another thing. We're going to call it binary. Binary can be a binary digit, but it can be one or more binary digits, okay? So a binary digit is only a single character, and binary is made up of single characters, right? So we can either have one digit, 1 0, or we can have 0, or we can have more than 1 0. Ugh. Okay, so we're looking at the binary non-terminal. Oh, wait, this should be a great time. So, binary digit. We use this in this new rule called binary. And this is called a non-terminal. The reason why it's called a non-terminal is declared somewhere in our grammar, right? Which is binary digit. So we can check the definition of binary digit to see it's just the single character 0. So if we really wanted to, we could really substitute this for this, right? But we're not going to do that. We're going to keep it more abstract. So you have non-terminals and terminals. A non-terminal is something that has a definition, right? Binary digit has a definition already in our grammar. However, the 0 in the quotation marks is a terminal because it does not have a definition in our grammar. There we go. Yeah. Anyhow, so let's look at our grammar once more. So we're going to try to generate some text. So we're trying to generate binary, okay? So binary says that we can have a binary digit, so 0, or we can have more, or we can have, more than one, just one binary digit. So I can have 0, 0, or 0, 0, 0, or 0, 0, 0, 0. I can have an infinite number of zeros, and that's valid binary in my grammar because this plus sign says we can have at least one binary digit. But if we have more than just one binary digit, that's totally fine. So let's complete this. What we're going to add is or. So we're going to have, after the 0 in quotation marks, we're going to have a vertical bar, and then in quotation marks 1. Now, if you're familiar in Python, the or keyword, this is going to be very similar. We're going to say a binary digit can either be the single character 0 or the single character 1. So it can be either. So if we're looking at what a valid binary digit is, 1, oh, whoa, no, I didn't mean to press U, goodbye. If we want to see what a valid binary digit is, 1 is a valid binary digit, and 0 is a valid binary digit, okay? Hopefully that makes sense. And we can have more. If I wanted to have digits, right, this could be, say, 0, a 1, a 2, and in this case, digits could be either 1, 2, or a 3. Excuse me, I'm having a stroke. It'd be either a 0, a 1, or a 2, because I say it can be 0. The vertical bar means or, so it can be 0 or a 1, or a 1 or a 2. So it could be either a 0, 1, or 2. Hopefully that makes sense. Anyhow, so that there's that. We can have a 0 or 1. So now the thing is, with our grammar for what binary is, we can have a 0, or we can have more than just one single character. So say I want to mix it up and have another binary digit, that's a 1, and a 1, and a 0, and 1, 1, 0, and 0, 1, 1, there we go. And this right here is a valid binary in our grammar, right? So the plus sign says one or more of this thing, and in this case, we have, for a binary digit, we say it can either be a single 0 or a single 1, right? So we can have more than one 0 or 1, right? Now, say we wanted to be weird, and we wanted to have it could be 0 or more. For some reason, we want nothing, so absence of any 0s or 1s, be binary. I don't see why you would want that, because that makes no sense. But say you did. Say you wanted nothing to be valid binary. Sure, I won't judge you. I think it's weird, but sure. We would replace the plus sign with the multiplication symbol, because the multiplication symbol says 0 or more. So in this case, nothing, that's valid. That's a valid binary based on our grammar. Or we can say we want 1, 0, or 0, 0, 1, 0, 0, 1. Now, the difference between 0... I'm stuck in binary land. The difference between the plus sign and the minus sign is really important. You gotta grasp this. So this is 1 or more, and this is 0 or more. Okay? This is really important. Okay? You gotta grab... I'm dying today. That's a minus sign, Alastar. Okay. I'm making it. I'm going to make it. I swear. Yeah, so we have plus sign, 1 or more. Star symbol, that's 0 more, right? Multiplication symbol, 0 more. And now you can also have parentheses, okay? parentheses basically means it can, it groups things, right? So if I really wanted to, remove the binary digit terminal, or non-terminal, excuse me, I could have before the multiplication symbol, which notes 0 or more, in the parentheses I could say it could be a 0 or a 1. So 0 or more zeros or ones means that we can, is valid binary. So let's replace that with it. And now, please keep in mind, this isn't restricted to just binary, right? We could do something ridiculous, like if I wanted alphabet, right? My alphabet is going to be either A's or B's. And a word is going to be a cluster of A's and B's. So it's going to be one or more characters in my alphabet, right? And a sentence is going to be a word, and this is where parentheses. Well, no, that's dumb. I'm being dumb. No, the things in parentheses are just for grouping things. Don't listen to me. Or at least don't listen to that. So a sentence is going to be a word followed by a space, and I'm using uppercase in full caps to mean, hey, this is actually a space. I guess I could be, smart, and I could have a space, but whatever. We're going to have a space followed by another word, and the thing in parentheses is going to be 0 or more, okay? Now this is really important. So we're gonna go and look at an alphabet. Our alphabet can either be an A or a B. A word is a combination of one or more A's and B's. So we can have A, that's a valid word. B, that's a valid word. AB, ABBA, BBA, BBABA. These are valid words by our definition of what a word is. And now if we look at our sentence, we can have A, and then that's it. That's a valid sentence because we don't need to have a space and then another word because this is 0 or more, right? We have 0 or more spaces and then more words, right? So we can have at least one word in a sentence. Or we can have A, BBA, or BBBA, AB, AAA, BBB, ABBA, BBA, B. That these are valid sentences. Now the thing about this, the great thing about EBNF, which is really useful for making parsers, and I really should have said this earlier, is that in a finite way, right, in a textual format, I can exhaustively describe the grammar to an entire language. And these are exhaustive rules, right? If I wanted to, I could extend my grammar further. Why stop at single sentences? We could say that a paragraph, let's start with a paragraph. I'm just going to call it para, because I honestly don't know how to spell paragraph on the top of my head. But say we want to describe a paragraph, and that could be, maybe for our cases, we're going to have one or more sentences, okay? And this plus sign tells you that we're going to have one or more of this sentence. So a paragraph is one or more sentences, right? And hopefully you're able to see the power of this, where we're able to define something kind of cool, I guess. I don't know if it's cool, but you can hopefully see how you can describe a lot with this EBNF. Now, let's go and describe the grammar for a simple calculator program that will do addition, subtraction, multiplication, and division. Okay? So we're gonna do this real simple. We're gonna have a digit, and a digit is either going to be a 0, 1,
2, 3, 4, 5, 6, 7, 8, and 9.
Okay, that's a digit. We're going to have an integer, and an integer is going to be defined as one or more digits. Okay, so basically a bunch of digits is an integer. Now we're going to say we're going to have a, what are we going to have? We're going to have, let's start real simple. Let's talk about how we would add and subtract some things. Now earlier in my calculator thing, when I was talking about how to have, how to keep operator precedence in abstract syntax trees, you want the things that should be evaluated first to be lower on the tree. And we can kind of show how that works. We're going to have we're going to have an expression terminal. An expression is going to be a, let's see, we're going to have it be a term, and that term can be followed by a plus sign or a minus sign. We're going to wrap this all up. So we can have a term followed by a plus or minus symbol followed by another term, 0 or more times. So in this, if we take a look at what this generates, I'm using the double equals, I'm using this arrow symbol to show you what it can generate. What the sort of things that we can generate is just a single term, a term followed by another term that's being added, a term minus a term plus another term, etc., right? So we can have at least a single term, or we can add or subtract more than one other term. So we can have, whatever a term is, we don't know what a term is yet. We can have term, plus term, minus term, minus term, minus term, plus term, right? We don't know what a term is, but we can define that. So we can say a term is going to be a unit. It can either be a single unit, or after a single term, we can have a multiplication symbol, a division symbol, which is then followed by another unit. Okay. So the thing is, this is going to get really interesting. I can have a unit. I can have a term. I'm going to say x. I can have x be equal to a unit divided by another unit multiplied by a unit, right? We don't know what a unit is, but we can declare that, right? But notice that this x matches the definition of a term. Matches term definition is a term. So when we're talking about single expressions with this expression, definition, we can define this as being just x, because since x is our term in the expression, we just have a single term, so we just can keep x, or we can have x plus another term y, right? And that could be a unit times a unit or something like that, right? So if I was to totally expand this out, right? If I was to expand this out where I substitute x for the term, you can see, hey, we have a full-fledged or almost a full-fledged expression here. We're dividing a unit by a unit, multiplying it, and then we're adding that to a unit multiplied by another unit. Now, we still don't know what a unit is, but we're getting really close. Now, let me show you the magic. What I can do, if I wanted to end this and make it so our calculator is basically done, I can just substitute unit for an integer. And since we've already defined what an integer is, we have our calculator done. Well, it's a real simple calculator. We don't have parentheses, but this is the sorts of expressions that we can generate. So let's do this. So we can have a term Okay, what's a term? We can have an integer divided by dying. So we have this term because it's an integer multiplied by an integer. And since, again, we're saying we can have 0 or more integers multiplied or divided, we can have just 2, or 2 times 6, 2 times 6 times divided by 3. And now that we have that, we can say, okay, we have a single term. Do we have an addition symbol? Yeah, we do. So let's add another term. What's a term? We can have 2. And that's an entire term. And we have a full expression made. Now you might be wondering real quick, Alastar, how do I add parentheses so that I can have, grouping? We're going to replace integer with unit. And what's a unit? We're going to say unit is either an integer or, note this symbol, I'm just, bringing it to a different line and indenting it, but here I'll do first this way and then I'll show you the other way. And say we can either have an integer or an opening parentheses with an expression and a closing parentheses. You can notice here that we have a recursive nature here. And since we have an entire expression in the parentheses, we can have something like 1 plus 2 times 3 plus 6 times 7 plus 49. That is a valid expression because this set of parentheses has an expression in it, which has another set of parentheses, which has an expression in it, and so on and so forth, right? This sort of recursive nature that I was kind of talking about. And this is the same thing as just defining it on one line like this, but yeah. So that's the basics of EBNF. I hope that made sense. If you want me to use this to make another calculator program, I can do that for you guys if you want. But I thought this would be useful if you are interested in writing parsers and all that stuff. All right. Yeah, I'm Alastar, and I hope that you don't come upon a bug this evening. Goodbye.